section 2 of chapter 2. So we're talking about the derivative as a function. So that means like graphing the derivatives. So we can find the derivatives, right? F prime of a is the derivative. And so we can find that by taking the limit of the difference quotient, right, as h goes to 0. So that's the equation 1 or equation 2 or whatever. It's asking equation 2. So this is the derivative of f. And so we can graph this. Our x's stay x's. X's stay x's. And our normal y's. So our normal y values are the slopes. Okay, so normally you have your function, your normal function, so that'd be just f. And so you have your x's, and you have your y values, right? Y values. And so when we graph the derivative, our x's will be the same. So say if I have this point right here and this point right here. So there's my function. Say that's my function. And now I'm looking for the slope at, say, this point. Then my x for my derivative would be the same x2, but my y value when I graph the derivative, my y value would be the slope m at this point. So my x would stay the same, but my y value would be my slope at that point. So either of these forms, you can do a plus h or you can do x plus h. Those both are the same thing. So these mean the same thing, the derivative of f. Now, the domain is, like I said, your x's, but the domain of f prime, so the derivative, is all the x's as long as I have a derivative, or as long as the derivative exists at that point. So all the x's such that the f prime of x exists. Or in technical, you could go like that in set notation. All x such that f of x, f prime of x exists. So that means that, say if I have a function, and it looks something like this, so that at this x value, right, it's going on to infinity. So that means, say this is 2, then 2 would not be in our domain of the derivative, okay, because the derivative doesn't exist at 2, or if I'll get into it a little bit later, where all these actually happen at. So here we'll look at the graph of this function f. So here's our equation, y equals f of x, and we want to look at this figure and then sketch the derivative f prime. So we're going to sketch the derivative of f prime of this. So here's our function. So our x's are all going to be the same. So I have this x of 1. And then I just want to graph the derivative from this function. So my x's are going to be the same. So if I draw this, should have made this smaller. Okay, so my x's will still be the same. So I'll still have this value right here of 1, and so on. So my x's stay the same. It's just my y values are changing. Okay, so my y values are actually the slope. So slope in this direction, as I come down to this spot about right here, my slope is negative, right? Because I would have like a tangent line right there, and that slope would be negative because it's going down from left to right. Here it's negative. So that means if my slope is negative, that means my y values, which are my slope, so this would be a negative slope, this would be a positive slope. So your y values are just your slope. So I'm going down, so that means my slope is negative. So that means I'm coming up on the bottom, and right here it changes, right? It goes from negative slope to a positive slope, right? So I have this point right here. The slope is positive, the slope is positive. So I am positive, and then at 1, then I'm still positive slope, okay? And then at this point right here, I switch again. Now I come back to negative. So about right here, I switch to negative. So that means right here, I should be down here, correct? Because now my slope is negative. So that means I got to turn somewhere in here and come back because now I'm negative. So now I'm negative. And then I keep going negative, negative, negative slopes up until about right here. So right here, I'm going to start going positive, right? So I can just make a turn somewhere in here. We'll find out exactly where these values are that it kind of turns. But right here, I switch from negative to positive, 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 and it keeps on going positive. So then I just keep going positive. So it might look something like that. So we're just going to kind of do rough sketches. So we're looking at those turning points. So we look for those valleys, hills, valleys, and we mark those on our X's. Those will be our, oops, this one. So those ones will be where we cross zero at, right? Because here I have negative slope to positive slope to negative slope. So it's switching back and forth. So right there is where we switch from negative to positive. So that's how you graph the f prime of x. Because at these points right here, our slopes, if I have this point, my slope would be a horizontal line. Right here would be a horizontal line. And whenever we have a horizontal line, we have our slopes are zero, so that's why these are zero. So if we're looking at an equation, y equals f of x, right, here's the dependent variable. Right, it's dependent on what we choose for x, so x is our independent. We get to pick it. And y depends on what we choose for x, right? So this is our normal function notation, y equals f of x. So when we talk about the derivative, some other notations, so we've seen f prime of x, that means the derivative. Well, I can just do y prime. Those mean the same thing, the derivative. Okay, then we have some alternative forms. So f prime of x, the derivative, can also mean dy over dx. Dy over dx. So the bottom one is our independent variable, so that's what we put on the bottom. This is our independent variable. And our dependent variable is on the top. Now I can't remember whose form this is, dy over dx. I think it's Leibniz. And maybe Newton's is the f prime of x. I can't recall. But one of those two each had their own kind of form because they both kind of participated in putting together calculus. It's debated who actually created it, but Newton's more known for it, famous for it, but they were kind of both working on it. Okay, so we could also do this form. So the derivative of our function in terms of x. So this dy over dx means the derivative of y in terms of x, and df over dx is the derivative of the function, which is normally y, right, in terms of x. And then we can also do this, the derivative in terms of x of f of x, like that. It could be like that, or it can also be written d, the derivative of f of x, or it can be the derivative in terms of x of f of x, like that. So any of those forms will do. Most likely we'll stay with this one. Y prime is pretty easy. We'll get into this one, especially when we do implicit differentiation, because we can kind of treat that as a ratio and solve for dy. But we kind of won't right now, but later on we will. So here when we talk about differentiable, that's just meaning that talking about the function having a derivative. And the process of finding a derivative is differentiation. 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 So finding the derivative is the process of differentiation, and if it's differentiable, that means that the derivative exists. Okay, so there's some cases where the derivative exists, that means it's differentiable, and there's some cases that it does not exist, so it's not differentiable. So we kind of have three cases where it exists, or three conditions. So if it's differentiable at a value of x, so differentiable at a, differentiable at a, then it is continuous. At a. Then the contrapositive, if it is not continuous at a, then it is not differentiable at a. So as long as you can find the derivative at some x value, then it's differentiable at that x value. And if it's differentiable at that value, then it's also continuous at that value. And if it's not continuous, then it's also not differentiable. So if it's not continuous, which we already know from the last section, or last chapter, what it means to be continuous, right? So if it's not continuous, then it's not differentiable. So how can a function fail to be differentiable? That means it's not continuous. So if it's not continuous, then it's not differentiable. So just like your test in the last chapter, where is it not continuous? Well, that means if we have a hole, so we have a hole, if we have a jump, or if we have, we can be filled in right here as well, and it's still a hole. So it's not continuous, not continuous. Vertical asymptotes, like that, or you can go both ways. So these would be not continuous. So it's not differentiable. I keep spelling that wrong, but I'm not too worried about it. So if it's not continuous, it's not differentiable, right? But what if it is continuous? If it's continuous, then is it differentiable? Did I spell it right that time? So what about this? That's continuous, right? That's a continuous function, y equals absolute value of x. That means for every negative x value, I would have negative x, right? So that's everything smaller than 0, because I put in a -1, negative times a negative is positive, and I get a +1, right? -1, +1. It's a piecewise function. And then everything bigger than 0 is just x. Well, look at the slopes. This slope is going down, this slope is going down, this slope is going down, and then I go up, right? So right here at 0, the limit as x goes to 0 from the left is negative, right? -1. And the limit as x goes to 0 from the right is +1. So what's the overall limit then? If the left-handed limit equals something different than the right-handed limit, then what's the overall limit? Does not exist. So here I have a continuous function, but it's not differentiable because the derivative at 0 does not exist. So it's continuous at 0, but the derivative doesn't exist at 0. So just because it's continuous doesn't mean it is differentiable. If it's differentiable, then it's continuous, but not if it's continuous, it's differentiable. If that confuses you, sounds good. So now we can kind of add to this list a little bit. So we have holes, jumps, vertical asymptotes, and then we can also have any time that we have a kink, so like that, or also whenever we kind of have a vertical line. So if I have a vertical slope here, a vertical slope, my m is undefined, right? So that means the derivative would not exist. So jump, hole, vertical asymptote, as well as a vertical line for our slope, and any kind of kinks that happen. So those are where it's not differentiable. All right, so higher order functions, you might have, so we talked about maybe in the last video, the position function, and then its derivative, that was velocity. Don't put that, there we go, is velocity. And then so the derivative of that, which would be s double prime of t. So the second derivative of the position function would be the first derivative of velocity, which is acceleration. And then the third derivative, so we can just keep on taking the derivative and derivative and derivative. So the third derivative, 3, that'd be the second derivative of velocity. The first derivative of acceleration is jerk. So like it's like in a car, as soon as you press on the accelerator, it gives a lurch or it jerks. So the first derivative of acceleration is called jerk. And so those are some higher order derivatives. So we can just keep on taking the derivative.